The infimum of my wit is infinite. So let's talk about derivatives. First thing we want to define is something called the difference quotient. So if you've got a function f of x whose domain contains the point A, but also contains an open set around A. So A is in the domain of f, but so is a little open set around it. The difference quotient of f at A is defined to be this ratio right here, f of x minus f of a over x minus a, where these x's are typically going to be drawn from that open set containing a. But honestly, anything from the domain is okay. It's still the difference quotient. We are, however, going to want to take a limit as x approaches a. That's why we want to have this open set containing a in the domain of f. And indeed, one-sided things will come up. So once we've got this difference quotient, which is a fairly quick and silly little definition, the derivative of f at a is defined to be the limit as x approaches a of that difference quotient. So there it is. If that limit exists and is a real number, so not plus or minus infinity, that's what we call f prime of a, the derivative of f at a. Now, it is called the difference quotient because it's a quotient of two differences, but intuitively we will be able to understand it in the following way. So suppose this is a, okay, the interval of on which the function is defined, yeah, an open interval around a, great. So then what we have is we have this difference quotient, which was f of x minus f of a over x minus a. Now, this point right here, the x coordinate is a and the y coordinate is f of a. If I take another point, like this over here for some other value of x, I now have the point x comma f of x. Now if I connect these 2 points with a straight line, there we have it, the slope of that line is given by the difference quotient. So now what we do is we take a limit as x approaches a. Note, by the way, that x doesn't have to be bigger than a. If x is less than a, that's also totally fine. So if I take a limit as x approaches a, in a sense, what we're doing is taking a limit of slopes to somehow see what happens when we take that limit. What I'm not going to do, however, is call it a tangent slope. Now, some of you may have seen difference quotients defined before, but somewhat differently, involving an h. Observe that if I let x equal a plus h, and note that h doesn't have to be positive just because it's being added. It could be a negative number there. As x approaches a, that is equivalent to h approaching 0. So you can replace the difference quotient with what's given here below, and that's just making that substitution. X is a plus h, and x approaching a is equivalent to h approaching 0. And there it is. If you've seen it before, welcome back, old friend. Here are our one-sided limits. Okay, if you're only taking the limit as x approaches a from above, equivalently the limit as h approaches 0 from above, we call that the right derivative at a point, and similarly, if you take this left limit, we call that the left derivative at a point. This notation with the del with a subscript is not terribly commonly used, just because one-sided derivatives honestly are not discussed all that often, but there is the notation for it. Yep, we were expecting them to show up, and they did. So remember that when we talked about continuity on an interval or a set, if we had an end point of an interval, we could say continuous at that point if the appropriate one-sided limit existed. So similarly, we can say a function is differentiable on an interval if it is got a derivative on the interior and at the endpoints it has the appropriate one-sided derivatives. This is just totally consistent with how we've talked about things in the past. Don't call these half derivatives. Sometimes they'll be called semi-derivatives. I do prefer right and left derivatives. Semi-derivative is bandied about from time to time, but half derivative means something else. Yeah, so don't call them half derivatives when half derivatives are something else, which we will actually discuss. Much like when a certain limit exists, we said the function was continuous at a point. If that limit of the difference quotient exists and has a derivative, we will call the function differentiable at the point. And very similarly, if it's differentiable at every point in a set, we just say it's differentiable on the set A. So what we have here is a function. Okay, if a function is differentiable on a set A, then at every point we can compute its derivative at that point. This is a new function that says, given an input, output the derivative of f, and we call that function the derivative function. We'll typically use this f prime notation. We can also write it as df over dx, although it's not properly a fraction in our setting. No, nothing is different from when you've defined it before or studied it in Calc 1. We're just making sure that we're all on board with the original definitions. So let's do an example. The function f of x equals mx plus b is derivative on R. In other words, the derivative exists everywhere. And the derivative function is constant, and specifically it's the constant m. Yeah. No, we don't have a power rule yet, so we can't use it. Okay, remember, we're not using results we haven't proved. All we have is the definition of the derivative. But the proof is pretty straightforward. Okay, we want to take the limit as h approaches 0 of f of x plus h minus f of x over h, and this is at any given x in the real numbers. Well, f of x plus h distributes as just m times x plus h plus b, and then we take off mx and we take off b. So observe the mx's and the b's cancel, leaving behind mh over h. For any h which is not 0, we can cancel those h's off, and since we're taking the limit as h approaches 0, remember that you do not use 0 itself. Therefore, we're just taking the limit as h approaches 0 of the constant m, and constants have that value as their limit, so for any x, the derivative computes to be exactly m. Here's another example, and again, we're not going to be using any kind of power rule. Root x is differentiable for any positive number, and the derivative is 1/2 times x to the minus 1/2 power. So for any positive x, we start off by computing this difference quotient, g of x plus h minus g of x over h. Okay, since g is just the root function, then we get here just root x plus h minus root x. Now if I multiply the numerator and denominator by the algebraic conjugate of this numerator, which would be the root of x plus h plus root x, notice I haven't changed the value, we've only multiplied by 1, so this is just, silly little manipulation. But then what happens? We can see that in the numerator, once you distribute these terms out, you'll get exactly x plus h minus x, and the denominator is just h times this, which is down here. But now what happens in the numerator, those x's cancel out, leaving behind just an h, which I can then cancel with that one down in the denominator because h isn't 0. We're taking the limit as h approaches 0, so 0 itself, not an issue. And now we just have a 1 up in the numerator. And now we can just take the limit as h approaches 0. Okay, you can do this by just plugging in h equals 0 because the square root function is continuous. Now, if we wanted to take a right-sided limit at 0, because note the domain of g of x includes 0, but I only said it was differentiable on the interval that doesn't include 0. Now, at that left endpoint, we can take the right-sided limit. However, if you do, the limit will not be a real number, it will be positive infinity. And remember, we only said that derivatives existed when they were real numbers. Yeah. So work through the following here, and remember, don't use power rules or things like that if we haven't proved them. Use the definition. Okay, any comments or notifications, etc. you do on the channel really help me track how you guys are using these videos and how useful they are to you. Moving on. And yeah, we have now proved the power rule specifically when the power is a natural number. Okay, otherwise we still haven't got our general power rule. So here is a familiar result, and now we're going to prove it. Suppose a function has a derivative and is increasing. Then the derivative is not negative. Well, okay, I'd be careful about phrasing it like this, because we very consciously have avoided saying anything about the word tangent. So let's just dive right into the proof, okay? Since we assumed that f was differentiable, we know this limit exists. I don't know what it is, but I know it exists and is a real number. Now, just to be clear about things, f prime of a exists, which means I can take the limit as x approaches a, not just from one side of the difference quotient. But since that limit exists, it must be the same whether I take the right limit or the left limit. Okay, so the limit exists overall, therefore it is equal to the right limit as well, the derivative. So we're only taking the limit as x approaches a from above. That just makes it a little simpler to work with because I get to assume as x approaches a from above that x is bigger than a. Since f is increasing, if x is bigger than a, then f of x is bigger than f of a. So both the numerator and the denominator of that difference quotient are not negative numbers. So overall, the difference quotient is not negative, but it has a limit, therefore its limit can't be negative. And the limit of the difference quotient is just f prime of a. So f prime of a is not negative. If we're going to rely on some pictures to help guide our intuition, okay, then since I have an increasing function at any particular point a, I know that if I compute the difference quotient, I can take the limit from the right side or from the left side, and I'll get the same thing. So just to make our lives easier, ignore the left limit and work only with the right one. So now I have the point a f of a, and I'm going to look at a point x to the right and look at the point x f of x. Since the function is increasing, f of x is bigger than f of a, but also x is bigger than a because I'm only taking the one-sided limit. Therefore, our difference quotient f of x minus f of a over x minus a is not negative because it's a non-negative over a non-negative. This would be bigger than or equal to. And then since it has a limit and the difference quotient is never negative, the limit is also never negative, but that's just f prime of a. That's really all we've done here. Okay. Now there's a notion of linear approximation that can be very, very useful in many, many contexts. If f prime of a, aka the derivative, exists, then I'm going to define this function here, L of x. Notice this is just a line. F prime of a is a number. It's not varying with x. So this function L only varies with x, and it's a constant times x minus a plus some other constant. So it's just a straight line. It's called the linear approximation of f based at a, from which both of the following are very immediate. This first one is just the fact that I have a line, aka a polynomial of degree 1, it's continuous. So the limit as x approaches a of L of x is just what happens if I plug in x equals a, and that quickly evaluates to be f of a. But you can also divide L of x by x minus a, okay, and still end up with the limit f of a, and for that you're just going to rely on the definition of the derivative of the linear function. Now suppose f is differentiable at a point. Show each of the following. Here are some practice problems for you involving linear approximations and related results. Now that first one says, if the derivative exists and isn't 0, then you don't repeat values, at least on a little open interval around a. And for that, a proof by contradiction, I think, is the most straightforward. The second one says that if the derivative is 0, then for any epsilon which is positive, you can find a little neighborhood around a for which the following happens, and that just falls right out from the derivative definition. Okay, moving on. Here's another sample problem to work through. You can use traditional trigonometric knowledge of the sine function. You don't have to lean on it as a power series definition. Okay, but notice that the sine of 1 over x is not defined at 0, so we are manually declaring if you plug in x equals 0, f of 0 should be 0. Otherwise, use x squared times the sine of 1 over x. Prove that it's continuous everywhere, it's differentiable everywhere. Okay, that is fairly straightforward when x isn't 0, but at x equals 0, you have to be careful about how these things are computed. But the third point is really the interesting one, that the linear approximation based at 0 intersects the function infinitely many times, no matter how close you're looking to 0. Okay. And that third point really does destroy the notion of a tangent line. Traditionally, geometrically, we think of a tangent line as sort of touching the graph only once, at least if you zoom in far enough. And this third point here said we had a derivative and we used it to construct a linear approximation, but no matter how far you zoom in, near the origin, it will intersect the curve infinitely many times. It's very much not tangent in the geometric sense that we're used to thinking about. Well, so why do we call the derivative the slope of the tangent line? Under a lot of circumstances, it will have that property. Okay, this property that if you look close enough, then the linear approximation only intersects the graph once. In pretty general circumstances, that is a true statement, but it's not always true, as this example shows. Now let's revisit another old result that we're used to thinking about. Suppose f is differentiable on an open set A. Also, f of x is less than or equal to f of a for all x in this open set. In other words, f of a is a maximum value. Then the derivative at that point must be 0. So in the proof, we're going to take both left and right limits for these left and right derivatives. Okay, so our right derivative, which appears on the left there, since x is approaching a from above, x is bigger than a. Okay, but remember, f of a is bigger than or equal to every value of f of x. So in both limits, that numerator f of x minus f of a is less than or equal to 0, because f of a was the maximum value. However, the denominator changes sign. If x is approaching a from above, then x minus a is positive. If x is approaching a from below, then x minus a is negative. So I have a non-positive number in the numerator, and the denominator is on one side positive, but on the other negative. But the limit is assumed to exist and be equal. So our left bit there, the left term, which is the right-sided limit, that difference quotient is never positive, but it has a limit, so the limit can't be positive. Okay, if I'm taking the limit as x approaches a from the left, the numerator of the difference quotient is not positive, but the denominator is also not positive. So overall, the difference quotient is not negative, and since it has a limit, the limit can't be negative either. So the right derivative is less than or equal to 0, the left derivative is bigger than or equal to 0, but since we assume the function is differentiable, those two numbers have to be equal. And there's really only one choice for a number that is simultaneously less than or equal to 0, but also bigger than or equal to 0. It must be 0. So this is now an old result that we know. If you're at a maximum value, at least on an open interval containing the point where you're based, okay, because I had to take the limit from both sides. Okay, if you are at a maximum and you are defined and differentiable on an open interval, then the derivative at that point must be 0. The picture brings this together pretty quickly. Okay, so I have a function that's doing who knows what, but at x equals a, it achieves a value, and everything that happens on either side doesn't exceed that value. So when I take the difference quotient f of x minus f of a over x minus a, f of x is always less than or equal to f of a, so this numerator is less than or equal to 0. But if x is approaching a from above, then this denominator is bigger than or equal to 0. But if I'm approaching it from below, the denominator is also less than or equal to 0. So overall, my difference quotient is bigger than or equal to 0 for x less than a, but it's less than or equal to 0 for x bigger than a. So the limits from both sides tell me that f prime of a, since I'm approaching from above, I have difference quotients which are not negative, and this limit does exist, so the limit can't be negative. But if I approach from the left, I'll very similarly get this, and combining these tells me, aha, if I'm at a maximum, I have to have a point where the tangent slope, in big air quotes, is 0. So here are some sample problems to work with this notion of derivatives being equal to 0 or not. I realize that's a very general thing to say. The derivative is either 0 or it isn't. I strive to be useful. So hopefully you paused and worked through these problems and were able to show some stuff. Now let's talk about the relationship between a function being differentiable and it being continuous. If a function has a derivative at a point, then it is continuous at that point. Assume the derivative exists, call it L. Okay, here's a limit we can compute quite obviously. The limit as x approaches a of x minus a is definitely 0. So f prime of a is L, there it is. Multiply both sides by the limit as x approaches a of x minus a. Now on the right-hand side, we just get L times 0. But on the left, since both limits exist, the limit of the product is the product of the limits. And then I can cancel out those terms, x minus a over x minus a. And therefore, the limit as x approaches a of f of x minus f of a is 0. But since both the limit as x approaches a of f of x minus f of a exists, as does the limit as x approaches a of f of a, I can add that to both sides. Okay, and then since this limit and this limit exist, I can bring this limit inside and cancel it off there, giving me that last line. So differentiability is indeed stronger than continuity. This is the term we use when one thing implies another. We'd say it's stronger than it. So differentiability is stronger than continuity. Wherever you are differentiable, you must also be continuous. The reverse, not true. It's possible to be continuous but not have a derivative. Here's an example. The absolute value function is continuous at 0 but has no derivative at 0. We have established this function is continuous on the real numbers. We did that back several videos ago. Okay, so we already know it's continuous everywhere. Therefore, it's continuous at 0. Let's just address the question of its derivative. If I try to take the right derivative, okay, x is approaching 0 from above, so x is positive. If x is positive, the absolute value of x is just x. And then the x's cancel, and I'm taking the limit of 1, and I get 1. But if I take the left limit, I'm letting x approach 0 from below. Since x is now negative, the absolute value of x is evaluated as minus x to make it positive. Now I'm taking the limit of minus 1, and that has limit minus 1. Since the left and right limits don't equal each other, the limit overall doesn't exist, meaning the function is not differentiable at 0. It has a right derivative and it has a left derivative. It just doesn't have a derivative overall. Right, continuous functions can fail to be differentiable. That was the point of this example. Yeah, so imagine you have an absolute value-like function, but it goes up and then down and then up and then down and then up and then down and so forth, like a saw. Okay, it's continuous everywhere, but there are many isolated points at which it is not differentiable. Okay, so if the graph looks something like this, then it's continuous. You just have to replicate the proof of the continuity of absolute value. But at all of these corner points, it will fail to have a derivative. That's true. Can a continuous function have infinitely many points without a derivative? Well, the sawtooth example, if it extends, left and right, yeah, will fail to have derivatives at infinitely many points, all of its corners. You can even imagine something like this, a sawtooth. So here's the domain, okay, a nice compact interval. And the sawtooth does something, let me switch to a blue color, like this. One saw takes up half of the interval, okay? Then I put another saw in a quarter of the interval, then another saw in an eighth of the interval, then another one, and they keep getting narrower and narrower. So this function will be continuous, but not on the compact interval. It would have been, the way I've drawn it, it'll be continuous on this interval here. It won't be continuous at the right endpoint. But it will have infinitely many points where a derivative fails to exist, despite being continuous on a bounded set. Okay, you can even do more. Okay. The example I just drew lost continuity at the endpoint, but you can reclaim that. Put one saw, then put a second saw in half as much space, but also half as high. Then a third saw in half as much space, but also half as high. And so forth, and so forth, and so forth. Now the function will actually be continuous at both endpoints as well, and will still have infinitely many points where the derivative fails to exist. You can do lots of kind of crazy stuff here by squeezing in lots and lots of undifferentiable points. All the examples I've drawn, however, have the property that that the points where the derivative fails to exist are isolated from one another. You have a single point where the derivative fails to exist, and then you have a derivative for a while, and then you have another point where the derivative fails to exist. For a long time, people actually thought perhaps that's how it works. If you're continuous, at most, your derivative fails to exist on maybe isolated points. But Weierstrass, the same Weierstrass from before, came up with the following example, which is continuous everywhere, but differentiable nowhere. At no point does it have a derivative. So the points where the derivative fails to exist are very much not isolated. It's all of them. Okay. The proof relies on properties of derivatives combined with power series, because we're going to use the following power series written below. If you put certain criteria on how big the numbers an compared to bn can be, ans can control the amplitude of your cosine functions, where the bn's control the period. Basically, you want the amplitude to be small, but the period to be even smaller, so that the cosine functions are wiggling up and down very, very quickly. That's essentially how you're going to violate differentiability, but certain conditions on the ans are going to ensure continuity. Okay. So that will give us something that converges for all x. We define the function that way. Based on abstract properties of derivatives and continuity related to power series, you can show that this is under the suitable conditions on a and b, continuous everywhere and differentiable nowhere, but we're not really going to go through those details here. The graph looks like something like this. So an cosine of bnx has amplitude an, but period 2 pi over bn. So you take one cosine curve and you add to it something which has a much shorter period, but also a much smaller amplitude. So add to it something like this, and what you end up with is something that kind of goes like that. Okay, it's the original cosine curve shifted by this small adjustment, and now you add something to it that is even smaller but with an even faster period and so forth, and you keep doing that, and you end up with things here that look in a sense kind of fuzzy. They're going up and down crazy fast, but on very, very short ups and downs, and that crazy up down up down up down up down from the fast period prevents derivatives from converging, but the fact that the up down is not going very high does not interfere with continuity. Okay, I'm actually going to link here a video. Someone has made a wave file out of a Weierstrass function, and you can hear what it sounds like. And despite being such a crazy object, it actually sounds pretty normal as far as sounds go. It is a bit of a monstrosity from the analyst's perspective, though, but it was very helpful for nailing down that continuity and differentiability are really separate items, that differentiability is strictly stronger than continuity. If you're differentiable, you are definitely continuous, but it really can't go the other way in general. But yeah, it's not the most unreasonable thing. From a physical perspective, these power series of trigonometric functions are very natural objects to study. So this is not totally out of left field. And if you're really into finding the craziest examples you can, it's a really nice thing to get your hands dirty and play around with. So go ahead and look up other resources on the Weierstrass function if you find this interesting. We're just not going to cover it in these videos here, at least not yet. That's going to close out our definition of the derivative video. Of course, come back later. We're going to keep learning stuff. We're going to learn about properties of derivatives and what they're used for and what you can do with them.